Have you ever wondered how the lightning-quick Japanese bullet trains work? Yes, you got it right, by linear induction motor. In this presentation I will explain the basic working principles of the linear induction motor. Starting off with history. The history of linear induction motors can be traced back at least as far as the 1840s to the work of Charles Wheatstone at King's College in London, but Wheatstone's model was too inefficient to be practical. German engineer Hermann Kemper built a working model of linear induction motor in 1935, but it was not feasible. Then finally in the late 1940s, Professor Eric Laithwaite of Imperial College in London developed the first full-size working model. Professor Eric Laithwaite is now regarded as the father of maglev for his work in the field of linear induction motor and magnetic levitation rail system. A linear induction motor is an asynchronous linear motor that works by the same general principles as rotational induction motors, but is typically designed to directly produce motion in a straight line. In this type of motor, the stator is regarded as primary, which is connected to three-phase winding, thus stator is the armature in this motor, and rotor is regarded as secondary part which moves linearly. Stator and rotor of the three-phase squirrel cage rotational induction motor is cut along the section and laid on a flat surface to get primary and secondary part of linear induction motor. Primary part typically consists of a flat magnetic core with transverse slots that are often straight cut with coils laid into the slots, with each phase giving an alternating polarity so that the different phases physically overlap. The secondary part is frequently a sheet of aluminium. Some linear induction motors are double-sided with one primary on each side of the secondary. When the primary of a linear induction motor gets excited by a balanced three-phase power supply, a magnetic flux starts traveling along the entire length of the primary side. This linearly traveling magnetic field is equivalent to the rotating magnetic field in the stator of a three-phase induction motor. Electric current gets induced in the conductors of the secondary, which is rotor, then due to the relative motion between the traveling flux and the current-carrying conductors of rotor. Finally, induced current interacts with the traveling flux wave to produce linear force or thrust. When the three-phase supply is given, the synchronous speed of the traveling flux is given by Vs, which is stated in the slide. Synchronous speed depends on the supply frequency and the pole pitch. As stated earlier, there should be relative motion between the rotor conductors and the magnetic lines of flux, in order for a voltage to be induced in the conductor. That's why induction motors normally operate at a speed V that is slightly less than synchronous speed Vs. Slip S is the difference between the speed of traveling magnetic field flux and speed of rotor. For a slip of S, the speed of the rotor will be 1 minus S, multiplied by synchronous speed. Efficiency of linear induction motor is less than the efficiency of rotational induction motor, which is just because of unique phenomena which happens in linear induction motor. It is called end effects. It reduces the performance of motor at high speeds. End effects occurs as traveling magnetic field has non-uniform distribution near the ends of primary side, so currents induced due to those irregular magnetic flux are called end effect currents. Those currents produces additional forces causing braking action, by which efficiency of linear induction motor is decreased. Applications of linear induction motor. The main application of a linear induction motor is in transportation and in electric levitation systems, which are called maglev, like in bullet trains. Furthermore, this type of motor is used in the cranes and used for pumping liquid metals in industries. Actuators for the movement of doors also use linear induction motors. Thank you.